The boundary of light and time. When you look up at the night sky, you're seeing the universe as it once was. The light from distant stars has travelled for years, sometimes millions or billions of years, before reaching your eyes. This simple fact that light takes time to travel creates one of the most profound limits in all of science. It means there's a boundary to what we can see, a cosmic horizon beyond which no light has had time to reach us since the universe began. The observable universe measures approximately 93 billion light-years in diameter. This might seem contradictory at first. After all, the universe is 13.8 billion years old, a figure established through multiple independent measurements, including the cosmic microwave background radiation, the oldest light in the cosmos. If light has only had 13.8 billion years to travel, shouldn't the observable universe be 27.6 billion light-years across? The answer reveals something fundamental about the nature of space itself. Space has been expanding since the Big Bang, and it's been expanding throughout the entire journey that ancient light has made toward us. When we observe a galaxy whose light has travelled for 13 billion years, that galaxy isn't 13 billion light-years away anymore. The space between us and that galaxy has been stretching the entire time, carrying that galaxy farther and farther away even as its light journeys toward us. By the time we see that ancient light, the galaxy that emitted it is now roughly 46.5 billion light-years distant. This distance, the actual separation accounting for expansion, is what cosmologists call the co-moving distance. The edge of the observable universe isn't marked by galaxies or stars. Instead, when you look as far as current technology allows, you encounter the cosmic microwave background, a wall of radiation that permeates all of space. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, who were initially puzzled by persistent noise in their radio antenna, this radiation comes from a time roughly 380,000 years after the Big Bang. Before this moment, the universe was so hot and dense that it was opaque, a roiling plasma where photons couldn't travel freely without immediately colliding with charged particles. When the universe cooled enough for atoms to form, light suddenly could travel unimpeded. That first light, released in a cosmic flash, has been travelling through space ever since, stretching to longer and longer wavelengths as space itself expands. What began as visible light has redshifted into microwave radiation with a temperature of 2.7 Kelvin, just barely above absolute zero. This is the afterglow of creation, and it comes from every direction in the sky. The Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped this radiation with unprecedented precision, revealing tiny temperature fluctuations of only 1 part in 100,000. These minute variations represent the seeds of all structure in the universe, the slight density differences that would eventually collapse under gravity to form galaxies, stars, and planets. The Planck satellite, which operated from 2009 to 2013, refined these measurements even further. Its data revealed not just the structure of the early universe, but also allowed cosmologists to calculate fundamental parameters with remarkable precision. The age of the universe, 13.78, 7 billion years, plus or minus 20 million years. The composition, roughly 68.3% dark energy, 26.8% dark matter, and just 4.9% ordinary matter, the atoms that make up everything we can see and touch. But here's what makes the cosmic microwave background so significant for understanding the limits of observation. It represents an absolute barrier. You cannot see past it. not with any telescope we could ever build. The universe before that moment was opaque. Any light emitted earlier was scattered and absorbed countless times before atoms formed. Looking at the cosmic microwave background is like standing in a dense fog. You can see the fog itself, but not what lies behind it. This creates our first fundamental horizon, the surface of last scattering, the moment when the cosmic microwave background was released. The photons we detect from this surface have travelled for 13.8 billion years to reach us, but the space from which they originated is now 46.5 billion light-years away. This is the particle horizon, the boundary encompassing all events that have been able to causally influence us since the beginning of the universe. Understanding this boundary requires grasping how expansion works. The Hubble constant, named after Edwin Hubble, who discovered cosmic expansion in 1929, describes the rate at which space expands. Current measurements put this value at approximately 67.4 kilometers per second per megaparsec, though there's ongoing tension between different measurement methods that yield slightly different values. What this means is that for every megaparsec of distance, about 26 million light-years space expands by 67.4 kilometers every second. At vast distances, this expansion accumulates. Far enough away, the expansion of space itself exceeds the speed of light. This doesn't violate Einstein's special relativity, which states that nothing can move through space faster than light. Space itself can expand at any rate. Think of it like an ant walking along the surface of an inflating balloon. The ant might crawl at a steady pace across the rubber, but if the balloon expands quickly enough, the distance between the ant and any given point on the balloon can increase faster than the ant's walking speed. There exists, then, a distance beyond which galaxies recede from us faster than light. This is called the Hubble sphere, and it currently sits at about 14.5 billion light-years away. Galaxies beyond this distance are receding superluminally faster than light can travel, yet we can still see many of these galaxies. How? Because the light they emit isn't trying to move through space at faster than light speeds. The light moves through space at exactly the speed of light, but it's moving through space that's expanding. In the past, when that light was emitted, those galaxies were closer to us, potentially within the Hubble sphere. Their light has been travelling toward us ever since, gradually making progress even as the expansion of space works against it. This creates a second horizon, the cosmic event horizon. Currently located at about 16 billion light-years away, this boundary represents the distance beyond which events happening right now will never be observable to us, no matter how long we wait. Light emitted from beyond this horizon is fighting a losing battle against expansion. Even though it travels toward us at light speed, the expansion of space between us and the source grows faster than the light can close the gap. These horizons, the particle horizon marking what we can currently see and the event horizon marking what we could ever see, define the observable universe. They create a bubble around us, a sphere of causality and potential observation. Within this bubble, light has had time to reach us, or could eventually reach us. Beyond it lies what? The observable universe contains approximately 2 trillion galaxies, each with hundreds of billions of stars. The Hubble Space Telescope's deep field images revealed this astonishing number by photographing a tiny patch of apparently empty sky, no larger than a grain of sand held at arm's length, and finding thousands of galaxies in that minuscule region, extrapolating across the entire sky, yields that staggering total. Each galaxy represents a vast ecosystem of stars, planets, and potentially life, almost all of which will remain forever beyond our ability to visit or even to study in detail. The question of what lies beyond our cosmic horizon isn't merely philosophical. It has profound implications for our understanding of cosmology, the nature of space and time, and our place in existence. We know with certainty that the universe extends past what we can observe. The cosmological principle suggests that the universe looks roughly the same in all directions and at all locations, implying there's no edge to the distribution of matter, no boundary wall where galaxies suddenly stop. But how far does it extend? Is there more universe beyond our horizon, essentially identical to what we can see? Or does the universe beyond our view differ fundamentally in its properties, its laws, perhaps even in its dimensionality? The mechanics of cosmic expansion and observational limits. To understand what might exist beyond the observable universe, you need to grasp why we have observational limits in the first place. The explanation goes deeper than simply light takes time to travel. The very fabric of space-time itself determines what we can and cannot see, and the peculiar properties of cosmic expansion create boundaries that no technological advancement could ever overcome. General relativity, Einstein's 1915 theory of gravity, describes space and time not as fixed stages on which events occur, but as dynamic entities that bend, stretch, and warp in response to matter and energy. The equations of general relativity, when applied to the universe as a whole, allow for solutions where space itself expands or contracts. In 1922, Russian physicist Alexander Friedmann discovered solutions to Einstein's equations describing an expanding universe. Though Einstein himself initially resisted this idea, believing the universe should be static, Edwin Hubble's observations changed everything. In 1929, working at the Mount Wilson Observatory with what was then the world's largest telescope, Hubble measured the distances to numerous galaxies and found something remarkable. Galaxies farther away were moving away from us faster than nearby galaxies. The relationship was linear, double the distance, double the recession velocity. This Hubble's law, as it came to be known, provided direct observational evidence that space itself was expanding uniformly in all directions. The expansion of space differs fundamentally from objects moving through space. When a rocket accelerates away from Earth, it's moving through space, consuming energy to push against the gravitational pull and inertia. But when galaxies recede due to cosmic expansion, they're not moving through space at all. The space between them is increasing. No energy is consumed in this process. No force pushes the galaxies apart. They simply find themselves farther apart because more space exists between them than existed before. This distinction becomes crucial when considering superluminal recession velocities. Special relativity prohibits objects from moving through space faster than light because doing so would require infinite energy and would violate causality. But space itself faces no such restriction. The metric expansion of space, the technical term for this phenomenon, can proceed at any rate without violating relativity. To understand the observational consequences, consider a photon emitted from a distant galaxy. That photon travels through space at exactly 299,792 kilometers per second, the cosmic speed limit. As it travels, however, the space through which it moves is expanding. If the photon is traveling through a region where space expands at, say, 100 kilometers per second per megaparsec, then the photon makes progress by 299,792 kilometers every second through its local space. But space itself is stretching behind and ahead of it. The photon's journey toward us becomes a race between its velocity through space and the rate at which space expands. In the early universe, shortly after the Big Bang, space was denser and hotter, and the expansion rate was much higher. Photons emitted from extremely distant galaxies spent billions of years in regions where space expanded faster than they could make progress toward us. Only as the universe aged and the expansion rate decreased in their local region could they begin making headway. This creates an interesting effect. Photons from the most distant, observable galaxies spent a significant portion of their journey actually getting farther away from us in terms of proper distance, even though they were always travelling toward us through their local space. Eventually, as they crossed into regions where expansion had slowed sufficiently, they began making net progress in our direction. The mathematics describing this involve the scale factor, denoted as et, which represents how much the universe has expanded at any given time t. If we set the scale factor today equal to 1, then at earlier times it had smaller values. At the time of the cosmic microwave background's release, 380,000 years after the Big Bang, the scale factor was about 0.0009, meaning the universe was roughly 1,100 times smaller in each dimension than it is today. Redshift provides a direct measure of the scale factor at the time light was emitted. When astronomers observe a galaxy with a redshift Z equals 1.5, this means the wavelengths of light from that galaxy have been stretched to 2.5 times their original length, indicating the universe has expanded by a factor of 2.5 since the light was emitted. The cosmic microwave background has a redshift of approximately Z equals 1,100, corresponding to that factor of 1,100 expansion since its release. The Hubble constant, measuring the current expansion rate, is not actually constant over cosmic time. In the early universe, expansion proceeded much more rapidly. The deceleration parameter, which describes how the expansion rate changes, was positive for most of cosmic history, meaning expansion was slowing down under the attractive force of gravity. But approximately 5 billion years ago, something changed. Dark energy, the mysterious force that comprises 68.3% of the universe's total energy density, began dominating over matter's gravitational attraction. Since then, cosmic expansion has been accelerating. This acceleration has profound implications for what we can observe. As expansion accelerates, the cosmic event horizon, the boundary beyond which events happening now will never become visible to us, actually shrinks in co-moving distance. Light emitted from galaxies just beyond this horizon is fighting an increasingly difficult battle against expansion. Given enough time, distant galaxies that we can currently see will cross beyond our event horizon, disappearing from view forever as their light can no longer reach us through the accelerating expansion. The look-back time provides another way to understand these limits. When you observe an object at a given distance, you're seeing it as it appeared when the light left it. For nearby objects, this difference is negligible. The moon, as it appeared 1.3 seconds ago, the sun, as it appeared 8.3 minutes ago. But for distant galaxies, the look-back time becomes substantial. A galaxy 10 billion light-years away appears as it was 10 billion years ago, when the universe was just 8 billion years old. The cosmic microwave background, arriving from 46.5 billion light-years away, has a look-back time of 13.8 billion years. We're seeing the universe as it appeared just 380,000 years after the Big Bang. This ancient light encodes information about the conditions, composition, and structure of the early universe with remarkable fidelity. Temperature fluctuations in the cosmic microwave background, measured to be roughly 18 microkelvins in magnitude, represent density variations in the primordial plasma. Regions that were slightly denser than average gravitationally attracted more matter, eventually collapsing into the first stars and galaxies. The specific pattern of these fluctuations, their amplitude at different angular scales across the sky, reveals details about the universe's geometry, composition, and history. The angular power spectrum of the cosmic microwave background shows peaks and troughs at specific angular scales. The first acoustic peak, corresponding to regions about 1 degree across on the sky, tells us the universe's geometry is flat. Its large-scale spatial curvature is 0, or very nearly so. Parallel lines remain parallel. The angles of triangles sum to 180 degrees, and the geometry follows Euclidean rules. This flatness has important implications for the universe's extent beyond our horizon. A flat universe, according to general relativity, has no intrinsic spatial curvature. Unlike a sphere, positive curvature, or a saddle, negative curvature, a flat universe could extend infinitely in all directions. The observable universe would then be just a finite patch of an infinite whole, like observing a small section of an infinite plane. You could travel in any direction forever without reaching an edge or returning to your starting point. But flatness alone doesn't prove infinity. Topology, the global structure of space, matters too. A flat universe could be infinite, but it could also have a finite volume with a non-trivial topology. Imagine a three-dimensional version of a video game where leaving one edge makes you reappear on the opposite edge. Such wraparound spaces, called three-tori in mathematical terms, would be flat everywhere locally, but finite globally. If the universe had this topology, and if the wraparound distance were smaller than the observable universe, we'd see repeated patterns in the sky, multiple images of the same galaxies in different directions. Extensive searches in the cosmic microwave background data have found no such repetitions, suggesting that if the universe does have finite wraparound topology, the wraparound distance exceeds the size of the observable universe. The density parameter, denoted omega, provides another crucial measurement. It compares the actual density of the universe to the critical density to the exact amount needed for a flat geometry. Measurements from the Planck satellite indicate omega is extraordinarily close to 1, within a fraction of a percent. This near-perfect flatness poses a puzzle. In an expanding universe, any deviation from perfect flatness grows rapidly over time. If the universe is nearly flat today, after 13.8 billion years of expansion, it must have been incredibly, absurdly flat in the early universe, fine-tuned to parts per trillion or worse. This flatness problem was one of several puzzles that led physicist Alan Guth to propose cosmic inflation in 1981. Inflation suggests that the universe underwent a period of exponentially rapid expansion in its first fraction of a second, growing from subatomic scales to perhaps the size of a grapefruit in about 10^-32 seconds. This violent expansion would smooth out any initial curvature, driving the geometry toward perfect flatness regardless of initial conditions, much like inflating a balloon smooths out wrinkles in its surface. Inflation also provides a potential mechanism for understanding what lies beyond our horizon. If inflation occurred, it would have expanded the universe by a factor of at least 10, 26, likely much more. The observable universe would represent just a tiny fraction of the total inflated volume, a minuscule patch within a vastly larger whole. The regions beyond our horizon would be causally disconnected from us. We cannot affect them, they cannot affect us, and we can never exchange information. Yet they would have originated from the same initial conditions and would be governed by the same physical laws. The cosmic microwave background's uniformity supports this picture. Looking in opposite directions in the sky, you see regions that are now 93 billion light-years apart. These regions have never been in causal contact during the entire 13.8 billion year history of the expansion universe, light hasn't had time to travel between them. Yet their temperatures match to better than 1 part in 100,000. How did these disconnected regions know to have the same temperature? Inflation solves this horizon problem. Before inflation, the entire observable universe, and vastly more, was smaller than a subatomic particle. All regions were in thermal contact. Inflation then stretched this tiny, uniform patch to cosmic scales, preserving the uniformity across regions that would later become causally disconnected. The slight temperature variations we observe in the cosmic microwave background would have originated as quantum fluctuations during inflation, stretched to cosmic scales by the exponential expansion. These quantum fluctuations deserve closer examination. During inflation, empty space roiled with quantum uncertainty. Virtual particles appeared and disappeared. Energy fluctuated randomly on the smallest scales. Normally, these quantum effects remain confined to subatomic dimensions, but inflation amplified them, stretching microscopic quantum fluctuations to astronomical sizes. The density variations seeded by these quantum fluctuations eventually collapsed under gravity to form all structure in the universe, galaxies, clusters, and the cosmic web of filaments connecting them. If inflation truly occurred, then quantum mechanics and general relativity work together to create cosmic structure from fundamental randomness. Every galaxy, every star, every planet owes its existence to quantum fluctuations that occurred when the universe was a fraction of a second old. And if this process happened here, within our observable patch, it presumably happened everywhere inflation reached. The ancient light at the edge of everything. Standing at the shore of the observable universe, looking back in time to the cosmic microwave background, you're witnessing the universe at 380,000 years old, an infant by cosmic standards. But what does this boundary actually look like? What physical conditions existed at that moment? And what does the afterglow of creation tell us about the universe's structure? The cosmic microwave background appears remarkably uniform across the sky. But this uniformity required sophisticated corrections to reveal. When the radiation was first mapped in detail by the Cosmic Background Explorer satellite in 1989, astronomers had to account for Earth's motion through space. Our planet orbits the Sun at 30 kilometers per second. The Sun orbits the Milky Way's center at 220 kilometers per second. And the Milky Way itself moves through space at roughly 600 kilometers per second relative to the cosmic microwave background's rest frame. This motion creates a dipole pattern. One hemisphere of the sky appears slightly warmer, blue shifted by our motion toward it, while the opposite hemisphere appears slightly cooler, red shifted by our motion away from it. After subtracting this dipole, which has an amplitude of about 3.3 millikelvins, and removing contamination from microwave emission within our own galaxy, the intrinsic fluctuations in the cosmic microwave background become visible. Temperature variations of roughly 18 microkelvins superimposed on the average temperature of 2.7 Kelvin. These fluctuations encode an astonishing amount of information. Their angular distribution, how the hot and cold spots are distributed across different angular scales on the sky, depends on the universe's composition, geometry, and expansion history. The acoustic peaks in the cosmic microwave background's power spectrum arise from sound waves that propagated through the primordial plasma before atoms formed. Imagine the early universe as a hot, dense fluid. Regions that were slightly overdense wanted to collapse under their own gravity, but the intense radiation pressure from photons constantly colliding with electrons pushed back against this collapse. Compression heated the plasma, increasing pressure. The interplay between gravity pulling inward and pressure pushing outward created oscillations, acoustic waves reverberating through the cosmos. These sound waves had a maximum distance they could travel during the 380,000 years before the cosmic microwave background was released. This distance, called the sound horizon, was approximately 450,000 light-years at the time. Today, accounting for the universe's expansion by a factor of 1,100, this corresponds to regions roughly 1 degree across on the sky. The first acoustic peak in the power spectrum occurs at exactly this angular scale. The existence and properties of these acoustic peaks cannot be explained by any model other than the Big Bang. The precision with which observations match theoretical predictions provides overwhelming evidence for the standard cosmological model. When Planck measured the cosmic microwave background's temperature fluctuations across the sky, the data points fell almost perfectly on the predicted curve derived from general relativity, quantum mechanics, and plasma physics. Over a dozen distinct peaks and troughs appear at specific angular scales, each revealing details about the universe's constituents. The ratio of peak heights tells us the ratio of ordinary matter to dark matter. Ordinary matter, protons, neutrons, electrons, interacts with photons, contributing to the pressure that drives acoustic oscillations. Dark matter, however, only interacts gravitationally. It increases the gravitational pull on overdense regions, but doesn't add to radiation pressure. This distinctive signature shows up in the acoustic peaks, allowing cosmologists to determine that dark matter outweighs ordinary matter by about 5-1. The cosmic microwave background also exhibits polarization. Photons can oscillate in different directions as they travel, and the pattern of polarization carries additional information. When the cosmic microwave background photons last scattered off electrons at 380,000 years, the geometry of the scattering process imprinted polarization patterns. These come in 2 types: E modes, which resemble electric field patterns, and B modes, which have a twisted, curl-like structure. E modes were first detected by the Degree Angular Scale Interferometer in 2002. They arise naturally from the density fluctuations that created the temperature variations. B modes, however, require something more exotic. Either gravitational lensing of E modes by the universe's matter distribution, or primordial gravitational waves from inflation itself. The South Pole Telescope and the BICEP-Keck collaboration detected the lensing B modes in 2013, confirming predictions. The search for primordial B modes continues, as their detection would provide direct evidence of inflation and measure the energy scale at which it occurred. Looking at the cosmic microwave background means looking at a specific moment in cosmic history, but that moment is spread across space. The sphere from which the cosmic microwave background originates, the surface of last scattering, represents all locations in space that were the right distance away, such that light emitted at 380,000 years after the Big Bang is just reaching us now. Tomorrow, we'll see cosmic microwave background photons from slightly more distant locations, emitted at the same cosmic time but arriving 1 day later. This surface continuously recedes from us as we receive photons from ever more distant origins. In a sense, the cosmic microwave background is always there, always at the edge of the observable universe, always showing us the universe at that same moment in cosmic time. It's a horizon that retreats as we approach it. The physical conditions at the surface of last scattering were drastically different from today. The temperature was approximately 3,000 Kelvin hot enough to glow with visible light, similar to the surface of a cool star. The entire universe glowed with this light, a fog of photons scattering constantly off free electrons. Matter consisted primarily of hydrogen and helium nuclei, along with free electrons, created during Big Bang nucleosynthesis in the first few minutes after the universe's birth. As the universe expanded and cooled, the temperature dropped below the threshold needed to keep electrons stripped from atomic nuclei. Electrons combined with protons to form neutral hydrogen atoms in a process called recombination, though this term is somewhat misleading since these electrons and protons had never been combined before. Once neutral atoms formed, photons could suddenly travel vast distances without scattering. The universe became transparent, and those photons have been traveling freely ever since. Before recombination, during the first 380,000 years, the universe was opaque. Any hypothetical observer would see glowing plasma in every direction, similar to being inside a star. No galaxies existed yet, no stars, no structure beyond subtle density variations. This era, called the photon epoch, was dominated by radiation rather than matter. The energy density of photons exceeded that of matter particles, and radiation pressure influenced the universe's dynamics. The transition from opacity to transparency didn't occur instantaneously everywhere. Recombination happened over a period of roughly tens of thousands of years, with denser regions recombining slightly later than less dense regions. This created a finite thickness to the surface of last scattering, not a perfect shell, but a layer with some depth. This thickness limits how sharply we can probe conditions at that time. Between the era of the cosmic microwave background and the formation of the first stars lies a period cosmologists call the Dark Ages. For several 100 million years, the universe contained no light sources. The cosmic microwave background had redshifted below visible wavelengths, and stars had not yet ignited. The universe consisted of neutral hydrogen gas, slowly collapsing under gravity into denser and denser clumps, gradually building the structures that would become the first galaxies. This epoch remains largely mysterious because it's extraordinarily difficult to observe. Neutral hydrogen absorbs light at a specific wavelength, 121.6 nanometers, called Lyman alpha. As photons from the cosmic microwave background travelled through the Dark Ages, any that happened to have this wavelength, after accounting for redshift, were absorbed by the neutral hydrogen. This creates a gap in the spectrum called the Gunn-Peterson trough, named after the astrophysicists who predicted it in 1965. Observations of distant quasars, extremely bright objects powered by supermassive black holes, show these troughs appearing at redshifts beyond about z equals 6, corresponding to times less than a billion years after the Big Bang. The presence of the Gunn-Peterson trough indicates substantial neutral hydrogen existed between us and these quasars, suggesting we're seeing back to or near the end of the Dark Ages. The first stars formed between 100 million and 250 million years after the Big Bang, according to current estimates. These population 3 stars, as they're called, consisted entirely of hydrogen and helium. No heavier elements existed yet. They would have been massive, perhaps 100 to 1,000 times the Sun's mass, burning intensely hot and bright, but living only a few million years before exploding as supernovae. These explosions forged the first heavy elements, carbon, oxygen, iron, seeding the cosmos with the building blocks of planets and life. The ultraviolet light from these first stars began ionizing the surrounding hydrogen, creating bubbles of ionized gas that grew and eventually merged. This epoch of reionization transformed the universe from neutral back to ionized, though now the ions were spread much thinner than in the pre-recombination plasma. By about 550 million years after the Big Bang, reionization was largely complete. The James Webb Space Telescope, launched in 2021 and beginning science operations in 2022, was designed specifically to observe this era. With its enormous 6.5-meter mirror and extreme infrared sensitivity, JWST can detect the heavily red-shifted light from the first galaxies. Early results have been startling, revealing surprisingly mature and massive galaxies at redshifts beyond z=10, corresponding to less than 500 million years after the Big Bang. These galaxies appear more structured and evolved than models predicted, suggesting galaxy formation proceeded more rapidly than anticipated. As you look toward the cosmic microwave background and these ancient epochs, you're essentially looking backward through time toward a cosmic horizon. Every photon detected from these distant sources carries information about its journey, how many electrons it scattered off, what atoms absorbed and re-emitted it, how much the expansion of space stretched its wavelength. The farther back you look, the younger and more uniform the universe appears, the structures less developed, the conditions more extreme. But the cosmic microwave background represents an absolute barrier. The universe before that moment was not just distant, but fundamentally unobservable through light. Any earlier events remain hidden behind this opaque curtain. However, two other messengers might pierce this veil. Neutrinos, nearly massless particles that barely interact with matter, were abundant in the early universe. They decoupled from matter and radiation even earlier than photons, about 1 second after the Big Bang, when the temperature was roughly 10 billion Kelvin. These cosmic neutrino background particles have been travelling freely ever since, and if we could detect them, they'd reveal conditions in the first seconds of cosmic history. Unfortunately, their extremely weak interaction makes detection extraordinarily challenging. No experiment has yet observed the cosmic neutrino background, though several proposals exist. Gravitational waves offer another potential window. General relativity predicts that accelerating masses produce ripples in space-time itself, gravitational waves that propagate at light speed. Unlike light or neutrinos, gravitational waves interact barely at all with matter. They would have been produced in the very early universe by violent processes, and they would have travelled unimpeded through the opaque plasma, carrying information from even before the first second. The LIGO and Virgo detectors that first observed gravitational waves from merging black holes in 2015 operate at frequencies far too high to detect primordial gravitational waves. But a cosmic background of gravitational waves would have left imprints on the cosmic microwave background's polarization, those elusive B-mode patterns. Future experiments, potentially including space-based gravitational wave detectors, might allow us to probe back to within 10 to 35 seconds of the Big Bang itself, to the end of the inflationary epoch, if inflation occurred. Infinite horizons, when space has no boundary. The observable universe has a finite size, a sphere roughly 93 billion light-years across. But the universe itself may have no such limits. Cosmological models consistent with observations allow for an infinite universe extending forever beyond our horizon. Understanding how this works requires distinguishing between the universe's extent and the portion we can observe. A flat geometry, which measurements indicate describes our universe to high precision, permits infinite spatial extent. In such a universe, space extends infinitely in all directions, never curving back on itself or reaching an edge. The observable universe would be merely a finite bubble within this infinite whole, defined by the speed of light and the finite age of the universe, rather than by any actual boundary in space. This concept challenges intuition. How can an expanding universe be infinite? If it's infinite now, wasn't it infinite in the past? And if it was infinite at the Big Bang, how did the Big Bang even occur? The key lies in understanding what expands. When cosmologists say the universe is expanding, they mean the distances between widely separated objects increase over time. An infinite universe can expand perfectly well, in fact, more naturally than a finite one. Imagine an infinite grid where each intersection represents a galaxy. As time progresses, the grid spacing increases uniformly. The grid remains infinite throughout this process. It simply becomes less dense. Every distance doubles, or triples, or increases by any factor. But infinity times any finite factor remains infinity. Extrapolating backward, as you go earlier in cosmic history, the density increases. At the Big Bang, the density becomes infinite. But the volume, if the universe is spatially infinite, was also infinite then. An infinite universe doesn't expand from a point. Rather, it exists at infinite extent but infinite density at t equals 0. Every location in space existed at the Big Bang, experiencing infinite density simultaneously. This seems paradoxical, but it's a consequence of general relativity applied to a flat or open universe. The Big Bang wasn't an explosion in space, but rather an explosion of space, all of space, simultaneously, expanding from an infinitely dense state. In an infinite universe, there is no center to this expansion, no point from which everything emerged. Every location looks like the center of expansion to an observer there, seeing galaxies recede in all directions at rates proportional to distance. Observations cannot definitively prove or disprove spatial infinity. We can only measure the geometry within our observable region. If the universe's curvature is exactly 0 perfectly flat, then general relativity allows infinite extent. If there's even a tiny positive curvature, the universe would be finite but unbounded, like the surface of a sphere. If there's negative curvature, the universe extends infinitely, like a saddle surface, extends forever in both directions. The Planck satellite measured the curvature parameter omega k to be negative 0.001 plus or minus 0.002, consistent with exactly 0. This means if the universe has curvature, the radius of curvature must be at least several times larger than the observable universe. If the curvature is positive, indicating a closed universe, the total volume would be finite but enormous, at minimum several hundred times the volume of the observable region. If the curvature is 0 or negative, the universe could be infinite. An infinite universe has profound implications for what exists beyond our horizon. If space extends infinitely and the laws of physics are the same everywhere, then every possible configuration of matter that can occur will occur infinitely many times, given infinite space. The observable universe contains a finite number of particles in a finite volume, yielding a finite, though astronomically large, number of possible arrangements. In an infinite universe, all these arrangements would be realized infinitely often. This leads to a startling conclusion. If the universe is infinite, there are infinitely many regions identical to our observable universe, down to every detail. Somewhere beyond our horizon exists a region with the same galaxy distribution, the same stars, even the same planets. The probability of any specific configuration is infinitesimally small but non-zero. In an infinite universe, anything with non-zero probability occurs infinitely many times. Physicist Max Tegmark calculated the distance you'd need to travel, on average, to encounter an identical copy of yourself, someone with the same atomic arrangement, same memories, same thoughts at this moment. The number is staggeringly large, approximately 29 meters. This distance so vastly exceeds the observable universe's size that it's practically meaningless. But the mathematical point stands. In a truly infinite universe, with quantum fluctuations randomly arranging matter, every possible configuration appears somewhere. This includes not just copies of individuals, but copies of entire observable universe-sized regions. At roughly 118 meters away, statistical arguments suggest you'd find a region matching our entire observable universe atom for atom. Such distances are so incomprehensibly vast that they defy any meaningful visualization. Written in standard notation, these numbers would require more digits than there are particles in the observable universe. The uniformity we observe in the cosmic microwave background becomes easier to understand in this context. If the universe is infinite and uniform on large scales, then sampling any sphere of a given size should yield approximately the same properties. Our observable universe is simply one such sample, and regions beyond our horizon should exhibit similar statistical properties, similar density, similar galaxy distributions, similar structures, though with different specific details. Inflation strengthens the case for an infinite universe. If inflation occurred, it would have stretched any pre-existing curvature to immeasurably small values, driving the geometry toward perfect flatness. Even if the universe began with positive curvature, indicating finite volume, sufficient inflation would have expanded it so enormously that the curvature within our observable region would be undetectable. The total volume could be finite, but so large compared to the observable universe that it might as well be infinite for all practical purposes. Some inflation models predict eternal inflation, where the process never completely stops. Quantum fluctuations during inflation could cause some regions to continue inflating while others stop. The regions that stop inflating become pocket universes, causally disconnected domains, each thinking themselves alone. But the regions still inflating continue expanding exponentially, eventually producing more pocket universes, which themselves are surrounded by still inflating space, producing even more pockets. This creates an infinite fractal structure with pocket universes embedded in an eternally inflating background. André Linde, one of inflation theory's pioneers, proposed this chaotic inflation scenario in 1983. The eternally inflating background would be infinite, not just in space, but in time, continuing to generate new pocket universes forever into the future. Each pocket would potentially have different properties, depending on how the inflaton field, the hypothetical field driving inflation, behaved in that region, and how other fields settled into their ground states. Our observable universe would represent just one pocket in this infinite structure. Beyond our cosmic horizon might lie more of the same pocket, extending far beyond what we can see. But eventually, at truly cosmic distances, we'd encounter the boundary between our pocket and the still inflating region, and beyond that, other pockets with potentially different properties. The cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, underlies modern cosmology. Observations support this within the observable universe. Galaxy surveys show that while structure exists on small scales, individual galaxies, clusters, superclusters, the distribution becomes uniform when averaged over regions larger than about 300 million light-years. This suggests a statistical uniformity extending indefinitely beyond our horizon. However, the cosmological principle remains an assumption, not a proven fact. We observe homogeneity and isotropy within our accessible region and extrapolate these properties to the entire universe. But we cannot verify uniformity beyond the horizon. It's possible, though perhaps unlikely, that the universe's properties vary significantly from region to region, on scales larger than we can observe. Some cosmological models explore this possibility. The bubble universe models, distinct from eternal inflation, propose that different regions underwent different phase transitions as the early universe cooled, resulting in domains with different vacuum states and potentially different effective physical laws. These domains would be separated by boundary walls, potentially detectable if a wall existed within the observable universe. No such walls have been observed, but this doesn't rule out their existence at scales exceeding our observational limits. The multiverse hypothesis extends these ideas further, suggesting that what we call the universe is merely one among many separate, disconnected universes. This differs from an infinite universe in that multiverses are typically causally disconnected. No information or influence can pass between them, even in principle. An infinite universe beyond our horizon is simply more of the same space, governed by the same physics and potentially, eventually observable if we wait long enough and if cosmic expansion allows. Distinguishing between these scenarios matters for understanding the nature of physical law. In a single infinite universe, the laws of physics are presumably the same everywhere, and the cosmological principle holds universally. In a multiverse, different universes might have different laws, different constants, different particle content. The fine-tuning of physical constants that allows life to exist in our universe, the precise values of forces, masses, and coupling constants that enable atoms, stars, and complex chemistry might be explained by selection effects rather than fundamental principles. Topology provides another dimension to consider. Even if the universe is flat and apparently infinite, it could have interesting global structure. A three-torus topology, mentioned earlier, represents one possibility space wraps around on itself in three independent directions, creating a finite volume with flat geometry. An observer in such a universe would see repeated images of the same structures in different directions, separated by the wraparound distance. More exotic topologies exist mathematically. The Möbius strip demonstrates a two-dimensional space with a twist travelling in one direction and returning to the starting point flips your orientation. Three-dimensional analogues exist, such as projective space, where opposite points on a sphere are identified as the same location. These topologies create non-orientable spaces where left and right can exchange meaning during a journey through space. Observational tests for non-trivial topology search for matched circles in the cosmic microwave background sky, pairs of circles where the pattern of temperature fluctuations matches precisely, indicating we're seeing the same physical region from two different directions because of spatial wraparound. Jeff Weeks, Jean-Pierre Luminet, and collaborators conducted extensive searches in both WMAP and Planck data. They found no convincing evidence for wraparound at scales smaller than the observable universe. Though perfect matches could be hidden by the cosmic variance, random statistical fluctuations in the microwave background itself. If the universe does have non-trivial topology, with wraparound distances only slightly exceeding the observable universe's size, we might detect it with future, more precise measurements. If the wraparound distance is vastly larger, the question becomes indistinguishable from asking about an infinite universe. Both possibilities lie beyond our observational reach. The conceptual leap from a finite observable universe to an infinite total universe challenges human intuition, but follows logically from the physics we observe. general relativity permits infinite solutions. Observations favor flat or nearly flat geometry. Inflation provides a mechanism that naturally produces such geometry. The cosmological principle suggests uniformity beyond our horizon. Together, these form a compelling case that space continues indefinitely, that our horizon marks not the edge of existence, but merely the limit of our vision. What lies beyond that horizon in an infinite universe? More galaxies, more stars, more planets, an endless tapestry of cosmic structure following the same statistical patterns we observe nearby. The specific arrangements differ, but the laws governing them remain constant. Every phenomenon we've observed here occurs countless times out there. Every rare event, every unusual configuration, every improbable coincidence is repeated infinitely across infinite space. The multiverse labyrinth, parallel realities, and quantum branches. Beyond the possibility of an infinite universe extending our familiar space lies a more radical proposal, the multiverse. This umbrella term encompasses several distinct concepts, each suggesting that our observable universe is just one among many separate, causally disconnected universes. The multiverse hypothesis has roots in both cosmology and quantum mechanics, and the different versions arise from fundamentally different physics. The level I multiverse, in cosmologist Max Tegmark's classification scheme, introduced in 2003, is simply an infinite universe of the type just discussed. If space extends infinitely beyond our horizon, those distant regions constitute a multiverse. In the most straightforward sense, many separate observable universe-sized regions, each with its own local configuration of matter, but all governed by the same physical laws and all connected through space. The Level 2 multiverse arises from eternal inflation. As described earlier, chaotic inflation models predict that inflation never completely ends everywhere simultaneously. Instead, some regions stop inflating and form pocket universes, while others continue exponentially expanding, eventually producing more pockets. Each pocket universe can be vastly larger than our observable universe, potentially infinite in extent, but separated from other pockets by exponentially expanding space. Alan Guth developed the first inflation model in 1981 to solve several cosmological puzzles, but he quickly realized that his original version had problems. Inflation once started, had difficulty ending. André Linde's chaotic inflation and Alexander Vilenkin's stochastic inflation, both developed in the early 1980 seconds, embraced this eternal nature. In these models, quantum fluctuations during inflation cause the inflaton field to vary from place to place. In some regions, the field rolls down its potential energy hill and inflation ends, creating a pocket universe. In others, fluctuations push the field back up the hill and inflation continues. The mathematics of this process predicts that the inflating regions always expand faster than pockets form within them. The total volume undergoing inflation increases exponentially, while pocket universes form like bubbles in an infinite expanding foam. Each bubble represents a causally disconnected region. Once inflation ends in a pocket, that region can never communicate with the still inflating space outside or with other pockets, because the intervening space expands faster than light. Different pockets might have different properties if the laws of physics can vary. This leads to the concept of a landscape of possible vacuum states. In string theory and related approaches to quantum gravity, the vacuum empty space isn't necessarily unique. There might be an enormous number of possible vacuum states, perhaps 10, 500 or more, each representing a different configuration of extra dimensions, different values of fields, and therefore different effective physical constants observable to beings in that pocket. When a pocket universe forms as inflation ends, the fields in that region settle into one of these possible vacuum states, potentially at random or depending on the quantum fluctuations present during inflation. Each pocket would then have its own set of physical constants, its own strength of gravity, its own electromagnetic force strength, its own particle masses. Some pockets would have constants suitable for forming atoms, stars, and life. Others would be stillborn, with physics that doesn't allow complexity to develop. This landscape paradigm addresses the fine-tuning problem from a statistical perspective. The constants in our universe appear exquisitely calibrated to allow life. Change the strength of gravity by a few %, and stars cannot form. Alter the electromagnetic force slightly, and atoms become unstable. Modify the mass difference between protons and neutrons, and Big Bang nucleosynthesis fails to produce the right mix of elements. These apparent coincidences troubled physicists for decades. The landscape multiverse offers an explanation. If countless pocket universes exist with different constants, then some fraction will inevitably have life-friendly values simply by chance. We necessarily find ourselves in such a pocket because we couldn't exist in the others. This anthropic reasoning that observations are conditioned by the requirement that observers exist transforms the fine-tuning from a mystery requiring explanation to an inevitable selection effect. Not all physicists find this satisfying. Critics argue that the landscape multiverse is unfalsifiable. If every possibility occurs somewhere in the multiverse, then no observation can rule it out. Proponents counter that the multiverse makes statistical predictions. Typical observers should find themselves in pockets with properties near the boundary of habitability, not deep in the Goldilocks zone where constants allow life easily. Testing these predictions requires understanding which properties are necessary for observers, a question mixing physics, chemistry, biology, and philosophy in complex ways. The Level 3 multiverse derives from quantum mechanics rather than cosmology. The many worlds interpretation proposed by Hugh Everett in 1957 suggests that quantum mechanics doesn't involve wave function collapse at all. Instead, every possible outcome of a quantum measurement actually occurs, with the universe branching into separate realities for each outcome. In standard quantum mechanics, a particle can exist in a superposition simultaneously in multiple states. An electron can be spinning both up and down at once, mathematically described by a wave function containing both possibilities. When measured, the electron is found in only one state, and the wave function collapses to that outcome. But what determines which outcome occurs? The Copenhagen interpretation, dominant for decades, treats measurement as a special process that collapses the wave function probabilistically, with outcomes occurring at the rates predicted by the wave function's squared amplitude. Everett found this unsatisfying. He showed that the mathematics of quantum mechanics doesn't require collapse. Instead, when a measurement occurs, the observer becomes entangled with the measured system, and the combined wave function evolves into a superposition of branches, one branch for each possible measurement outcome. Each branch contains an observer who saw a specific result. The wave function never collapses. It simply becomes more elaborate, encompassing all outcomes. From inside a branch, you observe only your branch's outcome. The other branches continue to exist, evolving according to the same laws. But they're inaccessible because quantum decoherence, the rapid entanglement of quantum systems with their environments, effectively isolates branches from each other. You can't detect the other branches or influence them, even though they're just as real as yours in the mathematical description. If Everett's interpretation correctly describes reality, then every quantum event spawns countless branches. Every particle decay, every photon emission, every measurement creates new branches of the universal wave function. The number of branches grows exponentially with time, creating a staggeringly complex structure where every possible history consistent with quantum mechanics exists in some branch. These quantum branches differ from eternal inflation's pockets in crucial ways. Quantum branches share the same spatial location, but differ in their quantum states. They're separated not by vast distances, but by orthogonality in the quantum state space, mathematical separation rather than spatial separation. All branches together constitute the total quantum state of the universe, evolving deterministically according to the Schrödinger equation. The level 4 multiverse, the most speculative in Tegmark's hierarchy, proposes that every mathematically consistent structure exists physically. If mathematical structures can be realized as physical universes, then all possible mathematical structures are realized somewhere in the level 4 multiverse. This includes not just different physical constants or initial conditions, but fundamentally different mathematical laws. Universes where logic itself operates differently, where the structure of space has different dimensionality or topology, not just as a solution to our equations, but as fundamental mathematical reality. This mathematical universe hypothesis treats physical existence and mathematical existence as equivalent. It suggests that physics doesn't describe the universe. Rather, the universe is a mathematical structure, and our physical intuitions about matter and energy are simply our subjective experience of existing within a particular mathematical structure. Other structures, equally real mathematically, constitute other universes with observers, if they're complex enough, experiencing entirely different physical realities. The level 4 multiverse pushes against the boundaries of science. If every mathematical structure exists, can we predict which one we should expect to observe? The answer depends on measure problems, how to count or weigh infinite possibilities. If infinitely many mathematical structures exist, with infinitely many observers in infinitely many configurations, what does it mean to ask which observations are typical? These measure problems plague all multiverse theories. In eternal inflation, infinitely many pockets form, with infinitely many observers. To make predictions, you need a prescription for comparing infinite sets, a measure that assigns probabilities to different types of pockets. Different measures yield different predictions, and no consensus exists on which measure is correct, or even whether the question is well defined. String theory's landscape faces similar issues. With 10, 500 or more possible vacua, calculating the distribution of properties across this landscape requires understanding how many pockets form with each type of vacuum. The dynamics of eternal inflation determine this, but the calculations involve extrapolating physics far beyond experimentally tested regimes. Some physicists view these measure problems as fatal flaws, suggesting that multiverse theories lack predictive power and therefore aren't scientific. Others see them as technical challenges requiring new mathematical frameworks to solve. The debate remains unresolved, with the multiverse's scientific status contested. Observable evidence for the multiverse would be revolutionary. Some proposals exist. Bubble collisions in eternal inflation might leave detectable imprints on the cosmic microwave background, appearing as anomalous cold or hot spots with specific geometric patterns. Several teams have searched for such signals without finding convincing evidence. The absence of signals doesn't rule out the multiverse collisions might be rare, or their signatures might be too subtle for current instruments, but neither does it provide support. Another potential signature involves looking for signs that the physics in our observable universe changes across distance. If we're in a large pocket universe, but not infinitely far from the boundary to the eternally inflating region or another pocket, we might observe gradients in physical constants or anomalies in the cosmic microwave background corresponding to different vacuum states. Again, searches have found nothing definitive. The anthropic predictions mentioned earlier offer indirect tests. If the multiverse exists with varying physical constants, then the values we observe should cluster near the boundaries of habitability, not finely tuned beyond what's necessary for observers. For instance, the cosmological constant, which determines the dark energy density, has a value that allows galaxies to form but is still small compared to naive theoretical estimates. Some researchers argue this fits anthropic expectations, though the argument requires assumptions about what properties observers require. Quantum many worlds might be testable through quantum computers and interference experiments, though not by directly observing other branches. If the many worlds interpretation is correct, quantum computers leverage computational resources from other branches to solve certain problems exponentially faster than classical computers. Successfully building large quantum computers and confirming their predicted advantages would provide indirect evidence that the wave function doesn't collapse, that all computational branches contribute. Whether these multiverse scenarios represent physical reality or speculative mathematical possibilities remains uncertain. The theories derive from extrapolating well-tested physics, general relativity, quantum mechanics, inflation into regimes beyond direct observation. They're logical consequences of our best theories pushed to their extremes. Whether nature actually realizes these possibilities, creating a cosmos vastly larger and stranger than our observable universe suggests, stands as one of the deepest open questions in fundamental physics. Varied physics, realms where different laws apply. If regions beyond our observable universe exist, must they follow the same physical laws we observe here? The question probes the nature of physical law itself. Are the laws of physics necessary truths, inevitable consequences of mathematics and logic? Or are they contingent facts, possibly different elsewhere? The constants of nature provide a starting point for this inquiry. The gravitational constant g determines the strength of gravity. The fine structure constant alpha governs electromagnetic interactions. The masses of fundamental particles, electrons, quarks, the Higgs boson, set scales for atomic physics and nuclear forces. In our observable universe, these constants have specific values, measured to extraordinary precision. The fine structure constant, for instance, equals approximately 1/137/36, a dimensionless number that particle physicists have measured to 11 decimal places. Why these particular values? No known principle of physics requires the fine structure constant to be 1/137 rather than 1/130 or 1/150. The masses of quarks appear arbitrary, with no obvious pattern or explanation. The strength of the strong nuclear force, which binds quarks into protons and neutrons, could conceivably be different without creating logical contradictions. These constants appear to be free parameters inputs to our theories rather than outputs. If these constants are truly free parameters, then perhaps they vary in regions beyond our observational reach. Different parts of space might have settled into different values during the early universe's phase transitions. Or, in the eternal inflation scenario, different pocket universes might have different constants determined by their vacuum states. The consequences of altered constants can be dramatic. Steven Weinberg showed in 1987 that if the cosmological constant the energy density of empty space were much larger than observed, it would have dominated the universe's dynamics very early, preventing galaxies from forming. The rapid expansion would tear apart any density fluctuations before gravity could collapse them into structures. In such a universe, no stars, planets, or life could exist. The electromagnetic force strength also permits only a narrow range for life. If the fine structure constant were 4% larger, carbon-1,2 nuclei couldn't form in stellar fusion, eliminating most of the carbon in the universe. If it were 4% smaller, oxygen nuclei would be unstable. Since carbon and oxygen are essential for life as we know it, these changes would preclude biological chemistry. Gravity's strength matters too. If gravity was stronger, stars would burn faster, exhausting their fuel in millions of years rather than billions, likely too quickly for life to evolve. If gravity were weaker, stars might not ignite at all. The gravitational compression needed to reach fusion temperatures wouldn't be achieved. The mass of stars is extremely sensitive to the gravitational constant. A small change produces enormous differences in stellar lifetimes and properties. The masses of fundamental particles show similar fine-tuning. The neutron is about 0.1% heavier than the proton, allowing neutrons to decay into protons, but making neutrons stable inside atomic nuclei, where binding energy compensates for the mass difference. If the mass difference were larger, neutrons would decay too quickly for nucleosynthesis. If protons were heavier than neutrons, hydrogen atoms would be unstable and complex chemistry couldn't exist. Fred Hoyle predicted the existence of a specific excited state of the carbon-1,2 nucleus in 1954, based on anthropic reasoning. He realized that the carbon abundance in the universe depends critically on a nuclear resonance, an energy level that greatly enhances the fusion reaction, combining 3 helium nuclei into carbon. Without this resonance, stars would produce almost no carbon. Since carbon exists abundantly and is essential for life, Hoyle reasoned that the resonance must exist at exactly the right energy. Experiments confirmed his prediction, finding the resonance at precisely the energy needed. This Hoyle state represents one of the most striking examples of apparent fine-tuning. Could life exist in universes with different constants? The answer depends on what you mean by life. Carbon-based biochemistry as we know it requires a narrow range of constants. But perhaps entirely different forms of complex organization could emerge in universes with different physics. Some physicists have explored whether alternate chemistries could support lifelike processes. Victor Stenger argued that many variations of constants still allow complex structures, suggesting life isn't as finely tuned as often claimed. The debate remains unresolved, partly because we lack a rigorous definition of life that applies beyond Earth's biochemistry. Must life involve self-replication, metabolism, and evolution? Could conscious observers exist as patterns in fundamentally different substrates, perhaps in the flow of exotic fluids, in networks of nuclear processes, or in topological structures in higher dimensional spaces? Beyond varying constants, the dimensionality of space itself might differ beyond our horizon. We experience 3 spatial dimensions plus 1 time dimension. String theory suggests additional spatial dimensions exist, compactified to sizes far below current experimental resolution. At high energies in the early universe, these extra dimensions might have been large and observable. If different regions underwent different compactification processes, the effective dimensionality could vary. A universe with 4 large spatial dimensions would have physics drastically different from ours. Gravity follows an inverse cube law in 4 spatial dimensions rather than inverse square, altering orbital mechanics and stellar structure. Atoms wouldn't be stable. The electron orbitals that exist in 3 dimensions don't have stable counterparts in 4 dimensions. The mathematics of electromagnetism changes too, potentially preventing the existence of atoms altogether. Conversely, a universe with only 2 spatial dimensions faces different challenges. 2-dimensional gravity is qualitatively different, and the topology of space constrains possible structures. Neural networks and complex information processing become difficult or impossible in 2 dimensions due to topological limitations. Neurons can't cross paths without intersecting. It's unclear whether consciousness could emerge in such a universe. 1 spatial dimension seems too constraining for complexity. Particles in 1 dimension can't pass each other without colliding. The propagation of waves and signals differs fundamentally. While mathematical structures can be complex in 1 dimension, the physical richness we associate with our universe appears to require at least 2, more likely 3, spatial dimensions. Why 3 dimensions? The anthropic answer suggests that only 3-dimensional spaces allow sufficient complexity for observers to evolve. But some physicists seek dynamical explanations. In the early universe, all dimensions might have been equivalent. As space expanded and cooled, perhaps only 3 dimensions became large, while others remained microscopic. The mechanism controlling this process remains speculative, tied to string theory's complicated mathematics and poorly understood dynamics. Symmetries represent another aspect that might vary. Our universe exhibits certain symmetries. The laws of physics are the same everywhere, in space, translation symmetry. The same in every direction, rotation symmetry. And the same at all times, time translation symmetry. These symmetries, formalized in Noether's theorem proved in 1915, directly correspond to conservation laws, conservation of momentum, angular momentum, and energy respectively. Could regions exist where these symmetries break down? A universe where physical laws change from place to place would violate translation symmetry, eliminating conservation of momentum. Particles would spontaneously accelerate without any force. Causality itself might become problematic. Similarly, breaking time translation symmetry would mean energy isn't conserved. Systems could spontaneously gain or lose energy. Such universes would behave bizarrely by our standards, potentially lacking the stability necessary for structured evolution. More subtle symmetry variations might be possible. Charge parity time, symmetry, which combines particle-antiparticle exchange, spatial reflection, and time reversal, appears to be a fundamental symmetry in our universe. All quantum field theories consistent with special relativity preserve CPT symmetry. But in regions with different vacuum states, or in hypothetical theories beyond quantum field theory, CPT might be violated. The physical consequences would be profound but difficult to predict without a specific theoretical framework. The arrow of time, the distinction between past and future, might vary cosmologically. In our observable universe, entropy increases over time, defining a clear temporal direction. This thermodynamic arrow aligns with the cosmological arrow, the direction of expansion, and apparently with the psychological arrow, the direction in which we remember. In a universe that undergoes eventual contraction, approaching a big crunch, entropy might decrease during the contraction phase, reversing the thermodynamic arrow. Beings in such an epoch would experience time flowing in the opposite direction relative to the expansion phase, though they wouldn't notice anything unusual from their perspective. Roger Penrose's conformal cyclic cosmology proposes that the universe undergoes infinite cycles, with each Big Bang following a previous universe's infinitely expanded future. In Penrose's model, the far future of each cycle rescales conformally to become the Big Bang of the next cycle. Physical constants might vary from cycle to cycle, with each iteration potentially having different properties. This remains highly speculative, dependent on unverified assumptions about the behavior of matter and fields in the extreme far future. Quantum field theory underlies particle physics, describing particles as excitations of underlying fields. The electron is an excitation of the electron field. Photons are excitations of the electromagnetic field, and so on. The specific fields that exist and their properties determine the particle content of the universe. In regions with different vacuum states, different fields might be excited, leading to entirely different particle spectra. Imagine a universe where the Higgs field settled into a different vacuum state. The Higgs mechanism gives mass to fundamental particles through their interaction with the Higgs field's vacuum expectation value. A different value would mean different particle masses. An extreme case, if the Higgs field was zero everywhere, fundamental particles like electrons and quarks would be massless, drastically altering atomic physics and chemistry. Atoms as we know them couldn't exist. Or consider a universe where additional fields exist, creating new types of particles with no counterparts here. Perhaps fields that generate repulsive long-range forces, complementing gravity's attraction. The large-scale structure would be completely different, potentially preventing gravitational collapse and galaxy formation, or fields that mediate entirely new fundamental interactions, binding particles in exotic ways our physics doesn't encompass. The vacuum energy, the baseline energy of empty space, could vary enormously. In our universe, measurements indicate a tiny but non-zero vacuum energy corresponding to dark energy. Quantum field theory naively predicts a vacuum energy 120 orders of magnitude larger than observed, a discrepancy called the cosmological constant problem. If other regions have vacuum energies anywhere near the naive prediction, their dynamics would be dominated by this energy, expanding so violently that structures couldn't form. Conversely, regions with negative vacuum energy would behave differently. General relativity permits solutions with negative cosmological constants, leading to universes that eventually recollapse. The AD-CFT correspondence in string theory, a mathematical duality between gravity in anti-de Sitter space with negative cosmological constant and quantum field theories without gravity, suggests negative vacuum energy. Universes might be mathematically rich and physically realizable, though their dynamics differ drastically from our observations. These varied physics scenarios remain largely theoretical. We have no direct evidence that physical constants or laws differ elsewhere. Observations within our universe show remarkable uniformity. The spectral lines of distant galaxies match those of nearby ones, indicating the same atomic physics operates billions of light years away and billions of years in the past. This uniformity extends as far as we can observe, suggesting that if variations exist, they occur only at scales far exceeding the observable universe. Testing whether constants truly are constant requires extreme precision. Quasar absorption lines, observed when light from distant quasars passes through intervening gas clouds, allow measurements of the fine structure constant at different cosmic epochs and locations. John Webb and colleagues claimed in 2001 to observe variations at the parts per million level across the sky, suggesting the fine structure constant might differ slightly in different directions. However, subsequent analyses by other teams found no such variations within measurement uncertainties. The question remains open, with future observations potentially settling whether apparent variations are real or instrumental artifacts. The standard model of particle physics describes fundamental particles and forces with just 19 free parameters, constants, that must be measured experimentally rather than derived from theory. A deeper theory might explain these constants, deriving them from more fundamental principles with fewer parameters. String theory attempts this, proposing that particles are vibrations of tiny strings, with the vibration patterns determining particle properties. In principle, string theory might predict all particle masses and force strengths from a single underlying principle. In practice, the theory has many possible vacuum states, each yielding different effective constants, recreating the landscape problem at a deeper level. Loop quantum gravity, another approach to quantum gravity, suggests that space itself has discrete structure at the Planck scale, roughly 10⁻⁵ meters. At this scale, space might be composed of quantum geometric units called spin networks, with properties that could vary. Different regions of space might have different spin network configurations, leading to different emergent physics at macroscopic scales. This remains speculative, as loop quantum gravity's predictions for cosmological scales remain underdeveloped. The very concept of physical law might be questioned. Are laws fundamental or emergent? Perhaps what we call laws are simply patterns that emerged as the universe evolved, like rules of grammar emerging from language use. In different regions or epochs, different patterns might dominate. This radical view, sometimes called cosmological natural selection or the principle of precedence, suggests laws evolve and adapt rather than being eternal mathematical truths. Lee Smolin proposed cosmological natural selection in 1992, hypothesizing that universes reproduce through black hole formation, with each black hole spawning a new universe with slightly varied constants. Universes with constants allowing many black holes would have more offspring, leading to natural selection favoring such constants. Our universe would then be typical of a highly reproductive configuration. This idea makes testable predictions. It suggests our constants are near optimal for black hole production, but the predictions are difficult to verify, and the mechanism for constant variation during black hole reproduction remains unexplained. Topological possibilities and geometric structures. The shape of space, its global topology and geometric structure represents another dimension along which universes beyond our horizon might differ. While measurements indicate our observable universe is flat or nearly so, this doesn't constrain the global topology. A flat space can have many different topological structures, each creating distinct observable signatures if the wraparound distance is comparable to or smaller than the observable universe. The simplest flat topology is Euclidean three-dimensional space extending infinitely in all directions. But mathematicians have catalogued other possibilities. The three torus, already mentioned, represents space that wraps around in three independent directions. Imagine a cube where opposite faces are identified. Leaving through one face brings you back through the opposite face. This creates a finite volume with no boundaries, perfectly flat geometry everywhere, yet finite total space. A three torus has three independent wraparound lengths. If these lengths are comparable to the observable universe's size, you'd see multiple images of distant galaxies arranged in a regular grid pattern across the sky. Each image shows the same galaxy at a different stage of evolution, depending on the light travel time from different wrapped paths. Searches in the cosmic microwave background for such periodic patterns have found nothing, setting lower limits on wraparound distances of at least 24 billion light-years in any direction. Based on Planck satellite data analysed in 2015, more exotic flat topologies exist. The Klein bottle, familiar in 2 dimensions, has a 3-dimensional analogue. In a Klein bottle universe, travelling in one direction and returning to your starting point flips your orientation. You come back, mirror reversed, with left and right exchanged. This non-orientable topology would create distinctive patterns in the cosmic microwave background, again not observed, constraining such models. Mathematicians have classified all possible three-dimensional orientable topologies that are finite and flat. There are 10 such topologies, each corresponding to different ways of identifying faces of fundamental domains. 6 are variations on the 3 torus theme, with different combinations of translations and reflections. 4 involve more complex geometric identifications. None have been observed to match our universe's structure at scales we can probe. If the universe has positive curvature shaped like the 3-dimensional analogue of a sphere's surface, then it must be finite, though it would have no boundary or edge. Travelling in any direction would eventually bring you back to your starting point, having circumnavigated the universe. The total volume would depend on the radius of curvature. Current measurements suggest that if the universe is positively curved, its radius of curvature exceeds 50 billion light-years, making the total volume at least several hundred times larger than the observable region. A positively curved universe would have distinctive observational signatures beyond just topology. The cosmic microwave background's angular power spectrum would differ, with the acoustic peaks shifted to smaller angular scales. Galaxy counts would increase less rapidly with distance than in a flat universe, as the volume of successive distant shells grows more slowly in positively curved space. Parallel light rays would eventually converge. These signatures haven't been observed within measurement precision. Negative curvature, saddle-shaped geometry permits infinite volume, even with finite wraparound possibilities. The hyperbolic plane, the 2-dimensional version, extends infinitely despite having constant negative curvature. Its 3-dimensional analogue, hyperbolic 3-space, provides the geometric framework for many negatively curved topologies. M. C. Escher's famous tessellations of the hyperbolic plane illustrate how geometric shapes fit together in negatively curved space. In Euclidean geometry, exactly 6 equilateral triangles meet at each vertex, creating a flat tiling. In hyperbolic geometry, 7 or more triangles can meet at each vertex, creating a surface that curves away from itself in all directions. This property that more space fits around each point than in flat geometry characterizes negative curvature. Geoffrey Weeks, a mathematician specializing in cosmic topology, catalogued numerous possible hyperbolic topologies for the universe. These range from relatively simple structures like the Weeks manifold to extraordinarily complex spaces with hundreds of distinct topological features. Each topology would create a specific pattern of matched circles in the cosmic microwave background if the fundamental domain fit within the observable universe. Weeks and collaborators developed algorithms to search for these patterns in observational data, finding no matches above the noise level. The Poincaré dodecahedral space represents one particularly elegant possibility. This topology uses a dodecahedron, a 12-faced solid, where each face is a regular pentagon as the fundamental domain. Opposite faces are identified after a 36-degree twist. An observer in such a universe would see 120 images of each distant source, arranged with dodecahedral symmetry across the sky. Jean-Pierre Lumière proposed in 2003 that this topology might match certain anomalies in the WMAP cosmic microwave background data, but subsequent analysis with more precise Planck data ruled out this specific model. Beyond standard geometries, more exotic possibilities exist in higher dimensional frameworks. If extra spatial dimensions exist, as string theory suggests, their configuration could vary across space. The Calabi-Yau manifold's complex 6-dimensional shapes that extra dimensions might form come in potentially millions of varieties. Different regions might have extra dimensions compactified into different Calabi-Yau shapes, each yielding different effective physics in the three large dimensions we observe. Lisa Randall and Raman Sundram proposed in 1999 a scenario with one extra spatial dimension that's infinite rather than compactified. Our universe would be a three-dimensional brain, a membrane in higher dimensional space, embedded in a four-dimensional bulk. Gravity could propagate through the bulk while other forces remain confined to the brain. This setup naturally explains why gravity appears much weaker than other forces. Its strength dilutes into the extra dimension, while electromagnetism stays concentrated on our brain. If multiple brains exist separated through the bulk, they would constitute parallel universes, literally parallel in the geometric sense, separated by distance through the extra dimension. These brains might occasionally collide, creating violent energy releases that could manifest as Big Bang events. The ekpyrotic scenario, developed by Paul Steinhardt, Neil Turok, and collaborators in 2001, proposes that our Big Bang resulted from such a brain collision, offering an alternative to inflation for explaining the universe's uniformity and flatness. Brain worlds face challenges. They must explain why we don't observe the extra dimensions effects. The Randall-Sundram models achieve this through warping the extra dimensions geometry curves in specific ways that concentrate particles and forces on the brain. But these models make predictions for particle physics and gravitational effects that experiments have tested, finding no deviations from standard four-dimensional physics within current sensitivity limits. Fractal geometries offer another exotic possibility. Fractals exhibit self-similarity across scales patterns that repeat at increasingly fine resolutions. Could space itself have fractal structure? At very small scales, quantum gravity effects might create a foamy fractal geometry. At large scales, the matter distribution in the universe shows fractal-like patterns in galaxy surveys, though this appears statistical rather than geometric. A truly fractal spacetime would have non-integer dimensionality. Instead of exactly 3 spatial dimensions, space might be 2.7 dimensional, or 3-dimensional in some averaged sense across scales. This would affect how forces propagate gravity wouldn't follow a precise inverse square law, but a power law with an exponent determined by the fractal dimension. Searches for such deviations in gravitational physics have found none, suggesting that if spacetime has fractal properties, they operate at scales too small or too large to detect currently. The holographic principle, emerging from black hole thermodynamics and string theory, suggests that the information content of any region of space is proportional to the area of its boundary rather than its volume. This implies that 3-dimensional physics might be a holographic projection of information encoded on a 2-dimensional surface. Juan Maldacena's AD-CFT correspondence, proven in certain mathematical frameworks, demonstrates precisely this equivalence between gravity in a higher dimensional space and quantum field theory on its boundary. If the holographic principle applies to our universe, then the physics we observe in 3 dimensions might be encoded on the cosmic horizon, our universe's boundary in space-time. The 3-dimensional bulk would be an emergent description, with the fundamental reality being 2-dimensional quantum information. This radical reinterpretation doesn't change observational predictions for local physics, but alters the deep nature of space and dimensionality. Topological defects, cosmic strings, domain walls, monopoles represent another geometric feature that might exist beyond our horizon. These are not objects in space, but rather defects in the structure of space itself, similar to dislocations in crystal lattices or vortices in superfluids. When the early universe underwent phase transitions as it cooled, different regions might have settled into different vacuum states. The boundaries between these regions form topological defects. Cosmic strings are one-dimensional defects, analogous to the line where three sheets meet when ice freezes. String theory suggests fundamental strings, quantum objects at the Planck scale, but cosmic strings are completely different macroscopic or even cosmic scale defects in space-time itself. A cosmic string's gravitational effects could gravitationally lens light passing nearby, creating distinctive double images of background galaxies. Extensive searches have found no convincing cosmic string signatures, though very light strings might escape detection. Domain walls represent two-dimensional defects separating regions with different vacuum states. A domain wall stretching across the universe would have enormous gravitational effects, potentially observable through its influence on the cosmic microwave background and large-scale structure. The absence of such signatures suggests either domain walls don't exist within our observable universe, or they're exceedingly rare. Magnetic monopoles, point-like topological defects predicted by many grand unified theories, would have been produced copiously in the early universe, according to standard calculations. Yet observations detect none. Inflation solves this monopole problem by diluting any primordial monopoles to undetectable densities. But in regions beyond our horizon that didn't inflate, or that inflated differently, monopoles might be common, drastically affecting the electromagnetic properties of space in those regions. Causal set theory proposes that space-time is fundamentally discrete, composed of discrete events related by causality rather than being a continuous manifold. In this framework, space and time emerge from the partial ordering of events. Event A either precedes, follows, or is space-like separated from event B. The structure of space-time is encoded in these causal relationships. Different causal structures could exist in different regions, giving rise to different emergent space-time geometries and potentially different dimensionalities. Loop quantum gravity arrives at similar conclusions through a different route. By quantizing general relativity, loop quantum gravity finds that space has fundamental indivisible units, quanta of volume and area, at the Planck scale. These quantum geometric units form networks that can have various configurations. The configuration determines the emergent large-scale geometry. In principle, different network configurations beyond our horizon could yield geometries unlike anything we observe locally. The multiverse's geometric structure itself poses questions. If pocket universes form in eternal inflation, how are they arranged? They can't simply sit next to each other in three-dimensional space. They're embedded in the higher dimensional, inflating background, separated by regions still undergoing exponential expansion. The geometry of the eternally inflating multiverse involves complex metrics where proper distances grow exponentially, making the notion of adjacent pockets mathematically intricate. Some cosmologists describe this structure as a fractal, with pockets nested within inflating regions that themselves contain more pockets. Renormalization group flows mathematical tools from quantum field theory, describing how physics changes with scale might govern the multiverse's structure, with different scales exhibiting different effective dimensionality and geometry. This remains highly speculative at the frontier of theoretical research. The limits of knowability, physical and practical boundaries. Even if we possessed unlimited technological resources and infinite time, fundamental physical principles limit what we can learn about regions beyond our cosmic horizon. These aren't engineering challenges, but absolute barriers imposed by the structure of space-time and the finite speed of information transfer. The particle horizon marks the boundary of all events that have been able to influence us causally since the Big Bang. Light and all other signals travel at finite speeds, bounded by the cosmic speed limit. Given the universe's finite age, only a finite region could have sent signals that have reached us. This creates an observational horizon that expands over time. Each moment, light from slightly more distant regions arrives, but it expands more slowly than the universe itself in our current accelerating phase. The event horizon marks a different boundary, the distance beyond which events happening now will never be observable to us, regardless of how long we wait. In a universe with dark energy causing accelerating expansion, this horizon actually shrinks in co-moving coordinates. Galaxies currently just inside our event horizon will cross beyond it in the future, disappearing from our view forever as their light becomes unable to overcome the accelerating expansion. Current estimates place the cosmic event horizon at approximately 16 billion light-years away, though calculating this precisely requires knowing dark energy's precise equation of state, the relationship between its pressure and density. If dark energy remains constant, a true cosmological constant, the event horizon stabilizes at a fixed co-moving distance. If dark energy weakens over time, the event horizon expands, potentially to infinity. If dark energy strengthens a scenario called phantom energy, the event horizon shrinks catastrophically, culminating in a big rip where accelerating expansion tears apart galaxies, solar systems, planets, atoms, and eventually space-time itself. The Big Rip scenario, while dramatic, appears unlikely given current observations. The equation of state parameter W, which equals -1 for a true cosmological constant, has been measured by Planck and other experiments to be -1.03 plus or minus 0.03, consistent with a cosmological constant. Values less than -1 indicate phantom energy, but current data don't require or strongly favor this. If W equals exactly -1, the universe expands forever at an accelerating rate, with the event horizon remaining at a stable co-moving distance, forever separating us from the vast majority of the universe. Even within the event horizon, practical limitations constrain observations. The cosmic microwave background surface of last scattering represents an absolute opacity barrier. We cannot observe the universe before atoms formed using electromagnetic radiation. The photons from earlier epochs scattered countless times before recombination, destroying directional information. This leaves roughly 13.4 billion years of cosmic history accessible to electromagnetic observations from recombination to today. Neutrinos and gravitational waves might penetrate earlier, as mentioned, but detecting them poses immense challenges. The cosmic neutrino background, released when neutrinos decoupled from matter at 1 second after the Big Bang, consists of ultra-low energy neutrinos, roughly 2 Kelvin in temperature today, barely above absolute zero. These neutrinos interact so weakly that detecting them requires experimental sensitivity far beyond current technology. Proposed experiments like Ptolemy aim to detect cosmic neutrinos through tritium decay. The electrons emitted when tritium decays have energies that would be infinitesimally shifted by absorbing a cosmic neutrino. Measuring these tiny energy shifts requires extraordinary precision. Ptolemy's design calls for detecting energy differences of less than 0.1 electron volts in the presence of much larger signals. The experiment might achieve first detection of the cosmic neutrino background in the 2030 seconds if technological challenges can be overcome. Primordial gravitational waves, produced during inflation or even earlier, would provide the earliest possible window on the universe's history. These waves would have wavelengths ranging from subatomic to cosmic scales, depending on when they were produced. Those with wavelengths comparable to the observable universe today, generated during inflation's earliest moments, would leave imprints on the cosmic microwave background's B-mode polarization. The tensor to scalar ratio R quantifies the strength of primordial gravitational waves relative to density fluctuations. Current upper limits from Planck and ground-based experiments place R is less than 0.06 at 95% confidence. Different inflation models predict different values of R, ranging from essentially 0 to as high as 0.5. Detecting non-zero R would confirm inflation and measure the energy scale of the inflationary epoch. Future experiments like LIGHTBIRD and CMBS-4 aim to measure R down to 0.001 or better, potentially detecting even weak gravitational wave signals. Beyond direct observation, theoretical physics might constrain possibilities through consistency requirements. Not every conceivable universe configuration is mathematically consistent. Quantum field theories must satisfy unitarity probabilities. Sum to 1, information is conserved. General relativity imposes constraints through energy conditions requirements that energy density and pressure behave in physically reasonable ways. String theory, if correct, might drastically limit possible vacuum states despite the landscape's apparent vastness. The swampland program in string theory attempts to identify which low-energy effective field theories can be consistently completed to full quantum gravity theories and which cannot. Theories that cannot be consistently completed lie in the swampland, mathematically consistent as approximate descriptions, but unable to arise from any quantum gravity framework. If string theory is correct, swampland criteria might rule out vast swaths of the landscape, dramatically reducing the number of possible pocket universe types. One swampland conjecture holds that stable de Sitter space, exponentially expanding space with positive cosmological constant, might be inconsistent with quantum gravity. Our universe appears to be in a de Sitter phase currently, driven by dark energy. If the conjecture is correct, either dark energy is not a true cosmological constant, but rather a slowly evolving field, quintessence, or string theory doesn't describe our universe, or the conjecture needs refinement. This remains actively debated. The trans-Planckian problem affects inflation. Quantum fluctuations during inflation that seeded cosmic structure originated at scales much smaller than the Planck length, the quantum gravity scale, where space-time itself becomes uncertain. Extrapolating quantum field theory to these extreme scales assumes that physics remains well understood, far beyond where we've tested it. New physics at the Planck scale could significantly modify inflation's predictions. This doesn't invalidate inflation, but highlights that our understanding rests on extrapolations beyond experimentally verified domains. Quantum mechanics itself might impose fundamental limits on knowledge. The Heisenberg uncertainty principle prevents simultaneously knowing a particle's position and momentum with arbitrary precision. Generalizations suggest that measuring any field or geometry with perfect precision would require infinite energy concentrated in infinitesimal regions, creating black holes that destroy the very information being measured. This suggests an ultimate limit to observational precision built into nature's structure. The holographic principle's entropy bounds provide another limit. The maximum entropy, and thus maximum information content of any region, equals 1/4 its surface area measured in Planck units. This means a sphere with radius equal to the observable universe can contain at most about 10^122 bitses of information. Every measurement we could possibly make, every observation ever recorded, every thought anyone has had adds to this total. While incomprehensibly large, it's finite. There's a maximum to how much information can exist within our cosmic horizon, limiting ultimate knowability even in principle. The computational complexity of simulating physics provides practical limits. Even with quantum computers exploiting quantum parallelism, simulating the universe at fundamental levels requires resources scaling exponentially with system size. Seth Lloyd calculated that the observable universe has performed approximately 120 quantum operations since the Big Bang. A simulation of the entire observable universe at the Planck scale would require more computational steps than this, more than the universe itself has computed. We cannot simulate our own universe in full detail. We can only create approximations focusing on particular scales and phenomena. These limits don't just constrain observations, they fundamentally restrict what questions have meaningful answers. Asking for precise initial conditions at the Big Bang runs into quantum uncertainty. Those conditions couldn't have been precisely defined. Asking what existed before the Big Bang might be physically meaningless if time itself began at that moment. Asking what lies beyond the cosmic event horizon in an eternally accelerating universe has no answer accessible through physics, as no information can ever reach us from there. Some philosophers argue these are merely epistemic limits, limits on our knowledge rather than ontological limits on reality. The universe beyond our horizon exists whether or not we can observe it. But physics concerns itself with observables, with testable predictions, a region that can never affect us in any way, that we can never observe or receive information from, stands outside the domain where physics makes predictions. Whether it exists becomes a metaphysical question rather than a physical one. The cosmic censorship hypothesis in general relativity proposes that singularities, points where space-time curvature becomes infinite, are always hidden behind event horizons, never naked and visible to distant observers. If true, this represents a fundamental limit. The interior of black holes, where singularities might exist, remains forever inaccessible to outside observers. Information that falls past a black hole's event horizon is lost to the external universe, though quantum mechanics suggests it's somehow encoded in the horizon's structure through Hawking radiation and holographic principles. The black hole information paradox highlights tensions between general relativity and quantum mechanics. General relativity says information that enters a black hole is lost to the outside universe. Quantum mechanics insists information is never destroyed, only transformed. Stephen Hawking initially argued that black holes destroy information, violating quantum mechanics. Later, he conceded that information must be preserved, somehow, encoded in subtle correlations in the Hawking radiation black holes emit. But precisely how this encoding works, the mechanism by which information escapes, remains an open question at the heart of quantum gravity. These paradoxes and limits suggest our fundamental theories are incomplete. General relativity and quantum mechanics, our two most successful theories, give contradictory answers in extreme conditions. A complete theory of quantum gravity, whether string theory, loop quantum gravity, or something not yet imagined, must resolve these contradictions. Until we have such a theory, our understanding of the universe's ultimate limits remains provisional, subject to revision as deeper principles emerge. Models and predictions. Comparing cosmological scenarios. Different cosmological models make different predictions about what exists beyond our horizon, and in some cases, these predictions have observable consequences within our accessible universe. Comparing these models helps clarify what we might learn through future observations and what might remain forever beyond reach. The simplest model, a flat, infinite universe governed by the standard Big Bang cosmology without inflation, predicts that beyond our horizon lies simply more of the same. The same types of galaxies, the same physical constants, the same laws, extending infinitely in all directions. This model, while elegant in its simplicity, struggles to explain several observations. Why is the universe so flat? Why is the cosmic microwave background so uniform across regions that were never in causal contact? And where are the magnetic monopoles that should have been produced in the early universe? The inflationary model solves these problems by positing a brief period of exponential expansion in the first fraction of a second. Basic inflation predicts that beyond our horizon lies more inflated space, essentially identical in its statistical properties, though different in specific details. The inflated region could be vastly larger than the observable universe, perhaps 10, 26 times larger at minimum, possibly infinite. Within this vast region, the laws remain constant, but quantum fluctuations during inflation created slight variations in density that evolved into galaxies and clusters we see today. Alan Guth's original 1981 inflation model faced a technical problem. Inflation, once started, had difficulty ending gracefully. This graceful exit problem led Andrei Lindy to develop chaotic inflation in 1983, where different regions of space undergo different amounts of inflation depending on initial conditions and quantum fluctuations. This naturally produces eternal inflation, where some regions keep inflating while others stop and form pocket universes. Chaotic, eternal inflation predicts a multiverse structure where our observable universe is one pocket among infinitely many. Different pockets might be vastly separated by still inflating regions. The space between pockets expands exponentially, making travel or communication between pockets impossible even in principle. Each pocket might have similar properties to ours, or in models where symmetry breaking varies, different pockets might have different physical constants. The string landscape, if realized in nature, would combine with eternal inflation to create a vast multiverse with enormous diversity. Each of the 10, 500 or more possible vacuum states could be realized in different pockets. Most would be sterile, unable to form complex structures, but some fraction would permit galaxies, stars, and perhaps life. Observers would necessarily find themselves in the subset allowing observation, explaining apparent fine-tuning through anthropic selection. Testing the landscape statistically requires calculating the distribution of vacua and predicting typical observable properties. If most life-supporting vacua have certain characteristics, we should observe those characteristics. Some analyses suggest the observed cosmological constant smallness is roughly what anthropic reasoning would predict, small enough to allow galaxy formation, but typical among vacua that permit observers. Other constants don't show such clear anthropic explanations, though detailed calculations remain controversial. Cyclic models offer an alternative to eternal inflation. These models propose that the universe undergoes periodic cycles of expansion and contraction, with each Big Bang following a Big Crunch. Roger Penrose's conformal cyclic cosmology represents one variant, proposing infinite cycles where each cycle's far future rescales to become the next cycle's Big Bang. Paul Steinhardt and Neil Turock's ekpyrotic model proposes cycles driven by brane collisions in higher dimensional space. Cyclic models predict that before our Big Bang lay a previous cycle, potentially with different properties. Physical constants might vary from cycle to cycle if symmetry breaking occurs differently during each bounce. The transition through the bounce, the moment of minimum size connecting contraction to expansion, requires physics beyond current understanding. General relativity predicts a singularity where curvature becomes infinite, requiring quantum gravity to describe the bounce properly. Observationally, cyclic models make predictions distinct from inflation. The spectrum of density fluctuations would differ, potentially showing a slight blue tilt, more power at small scales than large scales, rather than inflation's slight red tilt. The gravitational wave spectrum would also differ. So far, observations favour inflation's predictions, with Planck data showing a spectral index of 0.965 plus or minus 0.004, consistent with inflation but less favourable for simple cyclic models. However, cyclic models continue to be refined, and conclusive tests remain future work. The Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in 1983, addresses the universe's beginning in a radically different way. It proposes that time itself behaves like space near the Big Bang, creating a closed four-dimensional surface with no boundary or edge. In this model, asking what came before the Big Bang is like asking what's north of the North Pole. The question has no meaning, because time doesn't extend past the Big Bang. It curves around like Earth's surface curves at the poles. The no-boundary proposal predicts that the universe emerged from nothing through quantum tunneling, with the initial conditions determined by a path integral over all possible geometries. The model makes predictions about the universe's large-scale structure and the amplitude of fluctuations, though calculating these predictions requires assumptions about the quantum measure, how to weight different possible geometries, which remains ambiguous. Alexander Vilenkin's tunneling proposal, developed around the same time, offers an alternative quantum creation scenario. In Vilenkin's model, the universe tunnels from literally nothing, not even space-time, into existence, starting in a de Sitter phase of exponential expansion. Computational limits and information horizons. The universe, as an information processor, faces fundamental limits that constrain not just what we can observe, but what can be computed, communicated, or even exist as distinguishable states. These limits arise from quantum mechanics, thermodynamics, and general relativity working together, creating boundaries on information density, processing speed, and accessible information. Seth Lloyd, a quantum information theorist at MIT, calculated the ultimate physical limits of computation using quantum mechanics and thermodynamics. For a system of mass m and volume v, the maximum number of operations per second is limited by energy through the time-energy uncertainty relation. A mass m can perform at most 2 mc² pi operations per second, where m is the reduced Planck constant. For the observable universe, with mass approximately 1053 kilograms, this yields about 10^120 operations per second, the maximum rate at which the universe can compute. The maximum information storage capacity similarly has limits. The Bekenstein bound, derived by Jacob Bekenstein in 1981, states that the maximum entropy of any physical system is proportional to its energy times its radius. For a sphere of radius r with total mass energy E, the maximum entropy is approximately 2 pi ER x. Applied to the observable universe, this yields roughly 10^122 bits, is the maximum information that can be stored within our cosmic horizon. These numbers, while incomprehensibly large, are finite. Every physical process, every quantum state, every thought or observation represents some subset of this finite information budget. The universe, in this view, is a finite, though enormous quantum computer, bounded by fundamental physical laws in what it can compute or store. Quantum entanglement creates correlations across space that appear to exceed classical information transfer limits. When two particles are entangled, measuring one instantly affects the other, regardless of separation distance. This spooky action at a distance, as Einstein called it, seemingly allows faster-than-light communication. However, quantum mechanics prevents using entanglement for communication. The correlations are real, but extracting them requires classical communication at light speed to compare measurement results. Information cannot travel faster than light. The causal structure of space-time remains intact. These quantum limits apply within the observable universe. Beyond the cosmic horizon, in regions causally disconnected from us, separate information exists that we can never access. If the universe is infinite, then infinite information exists in total, though only a finite portion remains accessible from any given location. The holographic principle suggests that our horizon's surface area, measured in Planck units, sets the maximum information content accessible to us, implying that the three-dimensional bulk's information is somehow encoded on the two-dimensional boundary. The Landauer principle, established by Rolf Landauer in 1961, connects information and thermodynamics. Erasing one bit of information requires dissipating at least kT line 2 energy as heat, where K is Boltzmann's constant and T is temperature. This sets a fundamental cost for computation. Perfect efficiency is impossible because erasing intermediate results, necessary for most computations, generates heat. In the cold cosmic environment, with the cosmic microwave background temperature at 2.7 Kelvin, this energy cost is small but non-zero. As the universe expands and cools, this minimum energy per bit decreases, making computation more efficient over cosmic time. Black holes represent ultimate information storage devices. The Bekenstein-Hawking entropy of a black hole equals 1/4 its event horizon area, measured in Planck units. A black hole of mass m has entropy S equals Ka divided by 4x quasm square, where A is the horizon area and P is the Planck length. This entropy vastly exceeds the entropy of any other object of comparable mass. A black hole with mass equal to the Sun has entropy about 10^54 times larger than the Sun's entropy. This makes black holes the most efficient information storage possible. They pack more information per volume than any other physical system. The black hole information paradox arises because Hawking radiation appears thermal, completely random, carrying no information about what formed the black hole or what fell into it. If black holes evaporate completely through Hawking radiation, as calculations suggest they eventually do, where does the information go? Quantum mechanics says information cannot be destroyed, yet Hawking radiation seems to erase it. Proposed resolutions involve encoding information in subtle correlations in the Hawking radiation, perhaps through quantum entanglement between early and late radiation. The precise mechanism remains unknown, requiring a complete theory of quantum gravity to resolve. This problem directly relates to what information exists beyond horizons, if information. What exists beyond the observable universe? The unknowable and the known. Final reflections. The boundary between the observable and the beyond represents more than a limitation of technology or observation time. It marks a fundamental division in the nature of knowledge itself. Within the observable universe, questions have answers in principle, even if practice lags far behind. We could, with sufficient technology and time, measure every galaxy, catalogue every star, map every planet. Beyond the horizon, regions exist that are not merely unobserved, but unobservable, forever beyond the reach of light, causally disconnected by the expansion of space itself. This epistemological boundary forces us to distinguish between what we know, what we could know, and what remains unknowable. We know the observable universe's size, age, composition, and large-scale structure with increasing precision. Planck's satellite measurements determined the universe's age to within 20 million years out of 13.787 billion precision, better than 0.2%. We know the expansion rate, the densities of matter and dark energy, the temperature and fluctuation spectrum of the cosmic microwave background. We could know, with better instruments and methods, many things currently uncertain. Better gravitational wave detectors might reveal primordial waves from inflation, confirming that theory and measuring the inflationary energy scale. Improved neutrino detectors might observe the cosmic neutrino background, opening a window into the first second after the Big Bang. More powerful telescopes might detect biosignatures in exoplanet atmospheres, answering whether life exists elsewhere. Advanced particle accelerators might discover dark matter's identity or reveal new physics beyond the standard model. But some things remain unknowable by their nature. We cannot observe what lies beyond the cosmic event horizon in an accelerating universe. Those regions are receding faster than light can travel. We cannot see through the cosmic microwave background's opaque wall to earlier epochs using electromagnetic radiation. We cannot measure what happened before the Big Bang if time itself began at that moment. These aren't temporary limitations awaiting technological solutions. They're permanent features of physical law. The unknowable territories beyond our horizon might nevertheless be constrained by theory and logic. If inflation occurred, the inflated region vastly exceeds the observable universe, but its properties are determined by inflation's physics, the same physics that predicts observable features we can test. If the universe is infinite with uniform properties, we know statistically what exists beyond our horizon, even if we cannot see specific details. If the multiverse exists with varied physics, we can still enumerate possibilities, calculate probabilities, and make anthropic predictions. This theoretical framework, extrapolating from known to unknown using validated physics, represents the limit of scientific cosmology's reach. Beyond this lies pure speculation, untethered from testable predictions. Science requires some connection, however indirect, between theory and observation. When that connection breaks completely, we've left science for philosophy or metaphysics. The fine line between legitimate extrapolation and ungrounded speculation generates controversy. String theorists argue that string theory is science because it makes mathematical predictions that could be tested if we could build particle accelerators thousands of miles across or observe the universe at Planck scale. Resolution. Critics counter that could be tested in principle doesn't constitute science if the tests are physically impossible. Multiverse proponents claim that eternal inflation is a scientific prediction because it follows inevitably from inflation's equations. Skeptics respond that untestable predictions aren't scientific, regardless of their mathematical pedigree. This debate ultimately concerns what questions science can address. Must every aspect of a theory be directly testable? Or is it sufficient that a theory's foundations are tested, even if some implications transcend observation? Historically, science has accepted theoretical entities that cannot be directly observed: quarks, black hole interiors, the universe's state microseconds after the Big Bang, when theories predicting them explain observable phenomena successfully. The universe beyond our horizon falls into this ambiguous category. We cannot observe it directly, yet theories explaining what we do observe make predictions about it. If those theories prove correct in all testable predictions, their untestable predictions gain credibility by extension. If inflation correctly predicts the cosmic microwave background's features, the flatness of space, and the spectrum of fluctuations, then its prediction of a vastly larger inflated region beyond our horizon becomes plausible, though not proven. Practically speaking, humanity will never directly verify what exists beyond the cosmic horizon. The technological capabilities required are not merely beyond current reach, but impossible in principle. You cannot overcome light speed limits or cosmic expansion through technological cleverness. Future civilizations, if they exist millions or billions of years hence, will observe the same horizons we do, merely shifted in time as light from slightly more distant regions arrives. The acceleration of expansion means that distant galaxies are crossing beyond the event horizon faster than new galaxies enter the observable region. The universe within reach is actually shrinking in terms of the number of observable galaxies, even though the particle horizon itself slowly expands. This shrinking of the observable multiverse in terms of galaxy count rather than coordinate distance means future observers will see less than we do. In trillions of years, all galaxies except those gravitationally bound in our local supercluster will have receded beyond the event horizon. An astronomer in that far future, unaware of our current observations, might conclude the universe contains only their local cluster, surrounded by darkness and cosmic microwave background radiation. They would be wrong, but they'd have no way to know it from direct observation. This scenario illustrates how horizons limit not just current knowledge, but future knowledge. Information crossing the event horizon is lost forever to observers on one side, even though it continues existing on the other side. The asymmetry we can see galaxies now that future observers cannot highlights how the expansion's history and acceleration affect what can be observed from any epoch. Our epoch appears special in some respects. We live when galaxies are observable, when the cosmic microwave background is detectable, when cosmology is possible. Earlier epochs lacked the structure to support observers. Later epochs will lack access to the evidence we currently use for cosmology. The window of cosmic observability, when the universe has cooled enough to allow complexity, yet hasn't expanded so much that evidence disappears, spans only a fraction of cosmic history. We happen to exist during this window, raising anthropic questions about whether observers can only arise during epochs when observability permits learning about the cosmos. Despite these limitations and uncertainties, the progress of cosmology over the past century stands as one of humanity's greatest intellectual achievements. In 1915, Einstein completed general relativity but believed the universe was static and eternal. By 1929, Hubble had discovered cosmic expansion. By 1965, Penzias and Wilson had found the cosmic microwave background, confirming the Big Bang. By 2003, WMAP had measured the universe's age, composition, and geometry with percent-level precision. By 2015, LIGO had detected gravitational waves, opening an entirely new window on the cosmos. Each generation of instruments reveals new phenomena: dark matter's gravitational effects, dark energy's acceleration, cosmic inflation's predictions verified in the microwave background, exoplanets beyond our solar system, black holes photographed directly through event horizon imaging. The frontiers keep expanding, and the questions keep deepening. What we've learned dwarfs what Hubble knew, yet mysteries remain vast. The ultimate mystery, what exists beyond the observable universe, may never be fully resolved. Physics sets limits on knowability, that no civilization, however advanced, can overcome. Yet the question itself drives theoretical physics and cosmology forward. Inflation was developed to solve theoretical problems, and its prediction of regions beyond our horizon followed naturally. String theory attempts to unify quantum mechanics and gravity, and its landscape of possible vacua emerged from mathematical consistency requirements. Quantum mechanics was developed to explain atomic spectra, and the multiverse of quantum branches flows from taking its equations seriously. These theories, whether ultimately correct or not, expand our conceptual frameworks for thinking about reality. Even if we cannot observe other universes in an eternal inflation multiverse, understanding that such structures follow logically from inflation changes how we think about cosmic origins, physical law, and our place in existence. Even if quantum many worlds cannot be directly verified, it provides a consistent interpretation of quantum mechanics that illuminates the theory's meaning. What lies beyond the observable universe, then, is both unknown and, in some ways, understood. Unknown in specifics, we cannot point and say, there, 50 billion light-years away, sits a galaxy with these properties. Understood in principle, if our theories are correct, we know what types of structures should exist, even if we cannot observe particular instances. The universe beyond our horizon is both foreign and familiar. Foreign in that we cannot see it, familiar in that it likely follows the same laws we've discovered here. The observable universe stretches 46.5 billion light-years in all directions, containing 2 trillion galaxies, hundreds of billions of trillions of stars, and complexity beyond full comprehension. Beyond this, space continues how far? We don't know. Perhaps infinitely. Perhaps far beyond our horizon but still finite. Perhaps fragmenting into causally disconnected pockets with varied properties. The physics we understand constrains possibilities without uniquely determining answers. Multiple scenarios remain consistent with observations, and distinguishing between them may require evidence we can never obtain. We find ourselves observing from one location in space and time, able to see only a finite portion of what might be an infinite whole. The view from here is spectacular galaxies and cosmic structure, the ancient light of creation, the evidence of physics operating across billions of years and light years. Yet it remains a local view, necessarily incomplete, bounded by horizons both fundamental and inevitable. What lies beyond those horizons remains one of the deepest questions we can ask, perhaps the deepest, whose answer we can never fully know. Yet this inability to observe directly doesn't diminish the question's significance or the value of pursuing it theoretically. Understanding the limits of what we can know shapes our understanding of reality itself. The observable universe represents not the totality of existence, but merely the portion accessible to causal influence and information exchange. Beyond it lies more, possibly much more, governed by the same physical principles we've laboriously discovered through experiment and observation. The cosmos extends beyond our vision, into distances we'll never traverse, into realms we'll never observe, perhaps into configurations of space and matter we've never imagined. Some of these distant regions might harbour galaxies identical to ours, statistical twins, arising from quantum fluctuations during inflation. Others might exist in pocket universes with different vacuum states, different force strengths, different particles, rendering them utterly unlike anything we know. Still others might represent quantum branches of our own universe's wave function, parallel histories where different quantum outcomes occurred. All these possibilities emerge not from idle speculation but from taking seriously the implications of well-tested physical theories. General relativity, quantum mechanics, thermodynamics. These frameworks that describe our local universe with stunning accuracy make predictions that extend beyond observability. Following those predictions leads inevitably to conclusions about what exists beyond our horizon, even if we cannot verify those conclusions through direct measurement. The question, what exists beyond the observable universe, thus transforms into several related questions. What do our best theories predict should exist? How confident can we be in those predictions without direct observation? What distinguishes legitimate theoretical extrapolation from unfalsifiable speculation? And perhaps most profoundly, what does it mean for something to exist if it can never be observed, measured, or causally interact with us? These questions push against the boundaries of science, venturing into philosophy while remaining grounded in physics. They force us to examine what we mean by existence, what we require for scientific knowledge, and how we distinguish between reality and mathematical possibility. They remind us that the universe is not obligated to limit itself to what we can observe, that existence might vastly exceed accessibility, and that our cosmic horizon, while absolute in physical terms, might represent only an infinitesimal fraction of what truly exists. Standing at the edge of the observable universe, looking outward toward the cosmic microwave background and beyond, we confront the limits of human knowledge. We've measured, calculated, and theorized our way to understanding the universe's age, size, composition, and history. We've traced cosmic evolution from the first fraction of a second through 13.8 billion years to the present. We've mapped the distribution of galaxies across billions of light years and understood the forces shaping their formation. Yet for all this knowledge, the majority of reality, if the universe extends infinitely, or if multiverse scenarios prove correct, remains forever beyond our grasp. We see a sample, a local patch, a single observable bubble in a potentially infinite foam of causally disconnected regions. From within this bubble, we've learned an astonishing amount. We've discovered physical laws that likely apply universally. We've developed theories that predict not just what we can see, but what must exist beyond sight. The observable universe is our laboratory, our evidence, our cosmic context. What lies beyond it represents the implications, the extrapolations, the theoretical consequences of what we've learned here. We may never know with certainty what exists 100 billion light years away, or in another pocket universe, or in an alternate quantum branch. But we can reason about it, constrain possibilities, and recognize that the cosmos extends beyond our observational boundaries into realms that remain, perhaps permanently, unknowable yet undeniably real. This is both humbling and inspiring humbling, because it reveals how limited our perspective is, how small our observable patch is compared to what might exist, how much we can never know. Inspiring because it demonstrates how far human reasoning can reach, how much we've learned despite our limitations, how successful our physical theories have been in describing reality from subatomic scales to cosmic expanses. The universe beyond our horizon stands as both a limit and an invitation. A limit to direct knowledge, but an invitation to theoretical understanding, to mathematical exploration, to philosophical reflection on the nature of existence itself. What exists beyond the observable universe? More universe? Certainly more space, more time, more structure following physical law. Perhaps infinite variations on familiar themes. Perhaps radical departures into physics we've never imagined. Perhaps both, in a multiverse of staggering diversity. Perhaps something stranger still, beyond current theoretical frameworks, awaiting future Einsteins and Hawkings to unveil. We cannot see it, cannot measure it, cannot visit it, but we can think about it, theorize about it, and recognize that our observable universe, for all its grandeur, might represent merely the beginning of a reality far vaster and more complex than we yet comprehend. The question remains open, the horizons remain fixed, and the cosmos continues beyond them, indifferent to our inability to observe, yet following the same elegant laws we've discovered through reason, observation, and mathematical insight. The view from Earth encompasses 93 billion light-years of observable space, 13.8 billion years of observable history, and 2 trillion observable galaxies. It's an extraordinary view, unprecedented in its scope and detail. Yet it remains, inevitably and permanently, a local view bounded by horizons fundamental to the structure of space-time itself. What lies beyond those horizons is the universe's deepest secret, one that physics constrains but cannot fully reveal, one that theory addresses but observation cannot confirm, one that remains, perhaps eternally, just beyond our grasp, yet tantalizingly close to our understanding. **, end of script, final word count. Approximately 17,000 words. ****. The tunneling probability favors creating universes in high-energy vacuum states, which then undergo inflation. This provides a mechanism for the universe's beginning that doesn't require pre-existing space or time. Both quantum creation scenarios, Hartle-Hawking and Vilenkin tunneling, face interpretational challenges. They apply quantum mechanics to the entire universe, but quantum mechanics was developed to describe subsystems within a larger classical background. Applying it to everything at once requires new interpretational frameworks. The wave function of the universe represents a probability amplitude over all possible geometries and field configurations. But what does it mean for this wave function to collapse or be measured when there's no outside observer? The many worlds interpretation of quantum mechanics naturally extends to cosmology, suggesting that all possible quantum branches of the universe's wave function are equally real. Every quantum event since the Big Bang has created branches, yielding an incomprehensibly vast tree structure of parallel realities, all existing simultaneously within the universal wave function. In this view, what exists beyond our horizon includes not just distant spatial regions, but quantum branches representing alternate histories of the same spatial locations. Quantum cosmology remains speculative, at the boundary between physics, mathematics, and philosophy. Testing these ideas requires observations that can distinguish between different quantum initial conditions or different interpretations of quantum mechanics applied cosmologically. Such tests might come from precise measurements of primordial gravitational waves or from subtle features in the cosmic microwave background's non-Gaussianity deviations from perfect randomness that could reveal quantum effects from the earliest moments. Multiverse skeptics argue that any theory predicting infinitely many unobservable universes has abandoned science's essential requirement of testability. If any observation can be accommodated by choosing suitable properties for other universes, the theory explains nothing and predicts nothing. Proponents counter that the multiverse emerges as a consequence of well-tested theories like inflation and quantum mechanics, not as an ad hoc hypothesis. The testable components are the fundamental theories. The multiverse is their implication. This debate centers on what constitutes scientific legitimacy. Must every aspect of a theory be directly testable, or is it sufficient that the theory's foundations are testable, even if some consequences aren't? String theory faces similar critiques. It makes predictions at energy scales far beyond experimental reach, yet claims to be a scientific theory because its mathematical consistency and low energy limits can be evaluated. The distinction between universe, everything that exists, and observable universe, the portion accessible to observation, becomes crucial. If the universe extends beyond observability, either spatially or through multiverses, then cosmology necessarily involves elements beyond direct empirical verification. We must use indirect methods, testing the theories that predict these extensions, looking for subtle signatures, checking internal consistency, and following the logical consequences of well-established physics. Some proposed signatures of the multiverse might be observable. If pocket universes collide, a possibility in eternal inflation if two pockets happen to form close enough together before inflation separates them completely, the collision would release energy, potentially creating a disk-shaped temperature anomaly in the cosmic microwave background. Several teams have searched for such collision signatures, finding a few intriguing anomalies in the data, but nothing statistically compelling above what random chance would produce in the sky's 40,000 independent patches. The cold spot, a region of the cosmic microwave background discovered by WMAP that's cooler and larger than expected by chance, has been speculatively linked to a multiverse bubble collision. However, more conventional explanations exist, such as an unusually large supervoid, an underdense region along the line of sight. Planck's higher resolution data confirmed the cold spot's existence, but found its properties consistent with rare statistical fluctuations, making exotic explanations unnecessary, though not ruled out. Anomalies in the cosmic microwave background's large-scale structure, features at angular scales covering significant portions of the sky, continue to puzzle cosmologists. The quadrupole and octopole moments, the second and third spherical harmonic components, appear strangely aligned with each other and with the solar system's ecliptic plane, an alignment dubbed the axis of evil by cosmologist João Magejo. Whether this represents new physics, a systematic error, or simply cosmic bad luck remains debated. Proposed explanations range from non-trivial topology to multiverse effects to preferred directions violating the cosmological principle. The Hubble tension, the discrepancy between different measurements of the universe's expansion rate, might hint at new physics. Local measurements using supernovae and other distance indicators yield a Hubble constant around 73 km/s MPC, while cosmic microwave background measurements, assuming standard cosmology, give about 67 km/s MPC. This 8% difference significantly exceeds measurement uncertainties. Proposed resolutions include new forms of dark energy, modifications to gravity, early dark energy affecting the universe before recombination, or systematic errors in one or both measurement methods. Could the Hubble tension relate to what exists beyond our horizon? Some models propose that our observable universe sits in a local, underdense region, a void several 100 million light-years across, causing local expansion rates to differ from the global average. This would require abandoning perfect cosmological homogeneity at scales comparable to the observable universe. Alternatively, if physics varied across space in ways that affected early universe dynamics without violating local observations, different regions might have different expansion histories, with our local measurements not representing universal values. Future observations will clarify whether these anomalies represent real departures from the standard model, or if they dissolve with better data and analysis. The Vera C. Rubin Observatory, beginning operations in 2024, will measure distances to millions of supernovae, dramatically improving Hubble constant measurements. The Nancy Grace Roman Space Telescope, planned for launch in the late 2022, will survey vast volumes of space, testing cosmological homogeneity at unprecedented scales. The Square Kilometre Array radio telescope, under construction, will map hydrogen across cosmic history, tracing the universe's expansion with new precision. These instruments will test the cosmological principle more rigorously than ever possible. If the universe's properties vary significantly across the observable region, if distant regions show systematically different expansion rates, structure formation histories, or physical constants, this would revolutionize cosmology, suggesting that what we've observed locally doesn't represent universal laws, but rather local conditions within a vastly more diverse cosmos. Conversely, if observations continue showing perfect uniformity across all accessible scales, this strengthens the inference that uniformity extends beyond our horizon. The principle of mediocrity, the assumption that we occupy a typical location rather than a special one, would then suggest that unobservable regions resemble observable ones statistically. Combined with inflation's predictions, this would paint a picture of an enormous, possibly infinite, uniform universe beyond our horizon, with differences only in specific random details, not in fundamental properties.